We've finished igneous rocks, and we need to begin now with sedimentary rocks. In this photograph, you see a picture of the Grand Canyon, a famous location in the United States for beautifully horizontally bedded sedimentary rock, which has been cut through over time and eroded away by the present Colorado River, and it exposes the horizontal bedding of sedimentary rocks that were formed over a long period of time when sediment in a marine environment, the ocean, was slowly deposited, buried, compacted, cemented together, and finally lithified, which means in ancient Greek, rock, to be turned into a rock, to be lithified, from the ancient Greek lithos. And again, finally, we form these gorgeous bands of different colored rocks that make up the Grand Canyon. You can often see sedimentary rocks when you look out the car window while driving over the roads of America, because highway engineers have had to cut through rock to make the road, and those cuts will often reveal beautifully horizontally bedded deposits that became of sediment that became sedimentary rock, that were lithified. And again, the story of sedimentary rock, it becomes a story of the earth, because we know that the bottom layers are older than the top layers, and thus we can see how the environment changed, because each rock is a story of an environment of formation. A rock that has marine fossils tells you it was formed in an ocean environment, but a red sandstone may have been formed in an arid environment with more windblown sediments. So here you would have lots of water, here you would have very little. So sedimentary rock is very important in helping us understand the climate of the earth at the time of deposition of sediments that become the sedimentary rock. Here we have a marine environment that formed these magnificent layers of limestone in Lyme Regis, United Kingdom, and these layers are famous because they contain lots and lots of fossils. And of course, sedimentary rocks are important in our understanding of the history of the earth, because they are the rocks that contain fossils. Igneous rock and metamorphic rock will generally never, well, igneous never, metamorphic occasionally, but if you say you have found a fossil, you can be very near certain that you have found a sedimentary rock. What are some characteristics that tell you that you're looking at an igneous rock? You can answer that question. Using the reference table, explain what must happen in order for an igneous rock to turn into a sedimentary rock. You can answer that question. To begin with the process of how we make sedimentary rock, we just simply say that rocks are weathered and broken down. So this rock is broken down by wind or water, gravity, animals, into sediments, such as these in the photo, which are sand-sized sediments made up predominantly of a very hard mineral, quartz. Sedimentary, from the Latin, meaning to settle. The particles have been deposited. They are settling. Sedimentum. Rocks are weathered, again, one more time, by wind, water, and animals into sediment. The sediment is moved. The word we use for that is eroded. Erosion is the movement of sediment, or carried by the wind, water, and animals to a new place. And we should add here gravity. Gravity is an important part of the movement. So if I drop these rocks that are next to me, or if rocks fall down a cliff, that can create sediment, because the rock falling down the cliff breaks into smaller pieces and water washes it away. So gravity also. So we should say sediment is eroded by wind, water, gravity, and animals to a new place. Sediment is deposited, dropped in a new place. Sediment is then buried, compacted, cemented over millions of years to form the newly lithified sedimentary rock. And you have this given to you on page 6 of the reference table. It tells you very clearly that igneous rocks can be weathered into sediments. Metamorphic rock can be weathered into sediment. Sedimentary rock can be weathered into sediment. The sediments can be deposited, buried, compacted, cemented into a new rock called a sedimentary rock or sedimentary rock. Sedimentary rock is not the most common rock on the earth. Most rock is igneous because most of the ocean basin, the bottom of the ocean, is made up of igneous rock. And the basement rock of the continents is igneous rock, the very bottom rock. But the covering of the land surfaces on the earth are almost, well, 75% of them are covered by either sediments that are recently deposited, not yet rock, or the rocks themselves. To go back to our sediments in the hand of sand-sized quartz particles, we see that over time that sand-sized sediment can become a sandstone, which in this case has been carved into a beautiful Buddha in a cliff. So someone has carved the sandstone that had once been sand sediments that had come from some other rock. We often say in earth science, and in particular in geology, that the present is the key to the past. Because if you can observe certain phenomenon, this is not always true, but if you can observe certain phenomenon on the earth, for instance, the movement of sand at beaches or in deserts by the wind, you can look for the pattern that you see in the present with these layers of sand being deposited at this angle because wind was blowing sand over the top of this dune and then down the face, over the top and down the face until the wind changed and the predominant wind began to deposit sand in this horizontal fashion. Well, we can see this now looking at this actual sand dune somewhere. And then we can compare it with a rock that's millions of years old. And we can say, oh, this rock must have formed in a similar environment to this that we find today on the earth. So sedimentary rocks are very important in helping us understand the past. Textures of sedimentary rocks. Clastic, rocks composed of fragments or clasts. Clast just again means fragment, so a sandstone rock, a conglomerate rock, a breccia rock, a shale or a mudstone. These are clastic, land-derived, inorganic rocks. We have crystalline sedimentary rock. These rocks are formed due to the evaporation of saline water, so seawater becoming rock salt or gypsum. And then you have bioclastic, fragments again, but this time from life. So the fragments have come from living creatures. In this case, this is a rock that would be bioclastic. It's a combination of sediments and shells of formerly living creatures, and not just shells, but also crinoid stems, the stems of a particular organism. So bioclastic. Clastic or fragmental sedimentary rock, again, class or sediment from any type of parent rock make up what is known as a clastic sedimentary rock. And here we see the clasts. In this case, this is a breccia. So these are larger size fragments in a matrix of finer sand, silt, and clay. Clastic sedimentary rock is dependent upon the size of the sediments in order to be named. So if we have a rock made up of only clay, it has a particular name, shale. Only silt, siltstone. Only sand, sandstone. Only pebbles, cobbles, boulders in sand, silt, or clay, a conglomerate. And we can find the particle size for these different types of sediments here on this graph that's found on page 6 of the reference table. And we can see that if we go up, the particle diameter is here. We have clay going from the slowest that they give us is 0.0001 up to 0.0004 centimeters in diameter. Then silt ranges from this 0.0004 up to 0.006. These are silt-sized sediments. 0.006 to 0.2, sand-sized sediments. 0.2 to 6.4, pebbles. 6.4 to 25.6 centimeters in diameter, cobbles. And finally, anything over 25.6 is a boulder. And that's only about that big. So boulders are something you can probably carry in your hand, and then of course things that you couldn't possibly carry. Clastic sedimentary rock, here would be a conglomerate, because the clasts are big enough to be bigger. They're bigger than sand, and they're embedded in a matrix of smaller particles, and they're rounded, so it's a conglomerate. This is called a pudding stone. It's a famous conglomerate that's been placed on the battlefield of Gettysburg to memorialize the 20th Massachusetts Infantry, which fought there, and because it's a common stone from the Boston area. This is it polished, and you can see the clasts of pebbles and cobbles embedded in a matrix of sand, silt, and clay. Here's a breccia, angular particles in a matrix, and here's another conglomerate, rounded particles in a matrix, breccia and conglomerate. Here's a sandstone on the left, and you can see layering here, made out of particles that are sand-sized, and a siltstone made out of particles that are silt-sized. Sandstone, you can see I've taken some sandstone and banged it, and I've put particles of sand from the rock on the table in front. You can see particles here, and you can see particles here. These are classic sandstones that have a fairly high concentration of hematite. Hematite because of the sandstone's reddish color. Oil shale, a remarkable rock that has within it the remains of once living microscopic creatures that died, and whose organic matter was preserved in the shale, and from which today we recover oil that is then burnt in automobiles, buses, jets, buildings to make heat, electricity. This would be layers. You can see these horizontally bedded layers of sedimentary rock, and you can see one of them is a bed that has been identified as having a large concentration of oil shale, and that oil shale can be recovered. And this just gives you a little history of how oil would be formed. You have organic material that rains down, snows down onto the bottom of the ocean 300 to 400 million years ago. Over time, it's buried underneath impermeable rock and other sediments. The organisms are turned into the oil and natural gas and are trapped in the rock that forms. This then forms rock. And eventually you could drill down and recover that oil. We have limestones. How do we know it's a limestone? Well, in this case, we simply put a little bit of hydrochloric acid and we get the bubbling. Limestone is made out of calcite. The calcite has been either deposited from dead marine organisms or precipitated out of a solution of ocean water that has so much calcite in it that no more can be dissolved, and so it just sort of snows out to the bottom of the ocean. This typically happens in shallow, hot environments like the Bahamas today. The Bahamas are an example, again, of the past telling us about the present, telling us about the past, because we see limestone mud forming from precipitated calcite out of the ocean solution that will eventually be buried in millions of years and turned into a rock. Again, this is a fossil-bearing rock from Lyme Regis. We know it's limestone here, bubbling with acid here. A marine organism that was fossilized. I don't know where we got this, but you can see this is not inorganic. A living creature made these fantastic little holes. These are not vesicular rocks. This is not volcanic, and we know it's limestone because of the bubbling. Here's a piece of coral. I think I picked this up in Jamaica. Bubbling. Fossilized coral. Here's a piece of marine bioclastic limestone from upstate New York. And here we can see the individual shells that make up part of the matrix of this rock. We have a dolostone, which is a calcium carbonate with magnesium in it. And I wanted you to see this because you can see the distinct layering of this rock, so that the sediment is deposited in layers. And here is where I got the rock in New Jersey, the large formation of dolostone. And then up close we see again the laminae, the layering of the sediments. I think we'll stop here, and we'll say that anytime you see a fossil, you have a sedimentary rock. I think that's a good spot to stop.